In the same way that we have lots and lots of options when it comes to choosing a laser material, so we can, if we know roughly what wavelength we want, we can choose the right material. Once we've chosen our material, then we know which type of pump source we would have to use, and also then we can decide what type of resonator that we use, laser cavity that we use. So the one that we've seen so far is just a very basic two-mirror system, and that's referred to as a Fabry-Perot cavity. Just two plain mirrors, mirror 1, mirror 2, and the light bounces backwards and forwards between them. And one of the mirrors is referred to as HR, which is a high reflector, and one is referred to as OC, or output coupler. So the HR will typically be 100% or as close to 100% as you can, and the output coupler might have a reflectivity of between 80 and 90% so that we can actually extract some of the light from the laser. Okay. The energy density inside the cavities is usually very high, but the output, if we're only taking, say, 5% of the light coming out, then the other 95% will be bouncing around within the laser cavity itself. Now, we don't have to have plain mirrors. We can use curved mirrors, and we can use more than one mirror if we like. So there are some alternatives here, and again, I think Dr. Watson usually, in his part of the course, talks about resonator stability and things like that. So these are common stable resonator options. So plain and concave, plain mirror and a concave mirror. Spherical, so that the two the two mirrors have a radius which is equal to the distance between them. Confocal, where the mirrors have a shared focal point in the middle. And we can also fold the cavity so that we can bounce the light along and back along the same path, and we can thereby reduce the size of the cavity. So instead of having a cavity which is maybe this long, we can fold it back on itself so that it takes up less space on the bench. We can also have ring cavities, and we'll see this in one of the applications a bit later, where the light can travel around in a circle, or in a ring, sorry, and end up back where it started. And for these, you can have light which goes clockwise, and you can have light which goes counterclockwise, and that's an important feature of these lasers, as we'll see. This one's a figure of 8 cavities, so the light bounces about, and then again comes back to where it started from. Lots of cavity designs. One other fairly common item that you might find inside the laser, especially, well, for pulse lasers anyway, are what's called Q switches. So Q switches are ways in which we can try and build up much more energy inside the laser material rather than having it all come out at once, rather than having it coming out continuously. So it's to get very high peak powers. So if you want to do, for example, laser machining, then you might need very high peak energy in the pulse, or high peak powers, so that lots of energy over a very short time to facilitate that material processing. If we think about our two-level system again, level 1, level 2, we've got our energy coming in. So this is our input energy. And if the laser is working continuously, then what will happen is that atoms will be moved up into level 2, they'll fall down into level 1, and then go around that circle again. Okay, so you may have an energy level 3 up here, or you might have an energy level 0 down here. Okay. So again, let's think of this as being like a bucket with a hole in it that we're trying to fill up. So this energy level 2 is a bit like a bucket full of water, only we have a hole in the bottom, and I've drawn that far too big. So, okay. So the energy input is refilling the bucket. So that's energy level 2. And the water level here represents the number of atoms in the energy level 2. And what we've got is we've got a loss of that because of spontaneous emission, but also because of stimulated emission. Because we're generating photons in here, and so we're getting lots of stimulated emission. So we've got lots of energy going in, we're filling up the bucket, and the energy is being continuously drawn from it. So let's think about what would happen if we then block that hole. Okay, so now we've got to draw a deeper bucket. Only I can't draw straight lines, so I apologise. Wavy lines are okay, straight lines not so much. Let's supposing we've this was our original level when we closed that hole on the bottom. Then we've still got atoms coming into energy level 2, so we're filling that up, but they've got nowhere to go now. And so if we suddenly make a hole in the middle, then we get a massive pulse of energy coming out, lots and lots of atoms moving down from level 2 into level 1. Okay. Now how do we do that? Well, what we've got is we've got a laser cavity, and we've got our laser material, and we've got our energy coming into the laser material. And as long as the laser material can see the mirrors, then it will bounce backwards and forwards in resonance and give us some output. Let's supposing we put a shutter in here, let's supposing we block that off. Then what's happening is that we can't get the laser to work. The laser won't work because there's no resonance, there's no feedback. We've disconnected it from the feedback, but we've still got the energy coming in. Energy still building up inside this laser material. If we suddenly then remove the shutter, if we suddenly open that shutter, then all of the energy, oops, sorry, yeah, I've lost control. All of the energy which was been building up and stored inside this laser material will suddenly come out in one massive pulse. So we get a big pulse of energy coming out. Okay. So what we're doing is we're spoiling the quality of that cavity. So this idea of having a shutter in there is called Q spoiling or Q switching. So we switch the shutter open or closed, and that lets us build up energy, or it lets us dump all the energy out of the system. So the idea here is that we can essentially use it like an optical capacitor. We store lots and lots of energy into the system and then suddenly discharge it, suddenly dump all the energy out in one go. And the way that we physically do that is by blocking off one of the mirrors, essentially, or having it so that the mirror is not in resonance. Okay, so by removing the resonance condition, and then suddenly switching it back on again, then all of that energy is given out as a big pulse of energy with very high peak power. So it's lots of energy over a short period of time. Let's see, that's referred to as Q switching or Q spoiling. So the easiest way of doing that is obviously with a shutter to open and close it. But mechanical systems like that can't really be opened and closed very quickly. It's also very crude. And so another way in which you can do it is to have mirror 1, laser material, and then the other mirror can be spinning around. So that only once it gets into a correctly aligned position do you get your mirror giving you feedback and therefore giving you an output pulse. There are lots of other ways in which you can do this, much more sophisticated ways, and we can use acoustic waves to act as a switch on and off. We can use polarization, and we can use saturable absorbers. So in other words, if in here we had another laser type material, then we can have lots of atoms doing lots of absorption, and then when the power builds up enough, then we will have enough atoms up in level 2 in this material, in this slot here, not in the laser material, so that it suddenly then becomes transparent. But okay, I'm not going to go into them in any detail. Have a look online for yourself, just to, if you're interested, to see how they work.